Okay.
All right. So last day we started power series, and so we're going to continue today, but now we're going to show how to actually come up with our own power series. So last day I told you, here's a power series, let's analyze it, let's mess around with it, let's figure out where it converges. That's great. Today what we want to do is take functions and determine what their power series actually is. So the first thing, and this comes from a branch of mathematics called functional analysis, okay? Okay, just got new pens. Let it go, let's go. I just reloaded all of my pens, so I can't have a bad one. All right, so if f of x is analytic at x equals 0, then f of x is equal to now, the series that I just wrote on the right is expanded about 0 because it's in the form x minus 0 to the n. That's the most common type. Now, we need to define, this is one of the more important words, analytic. Okay, we use that term occasionally in calculus and heavily after calculus, but if you don't know what the word means, then you run into trouble because you'll see it. Analytic just means I can take derivatives and evaluate them at 0. So think of a polynomial, right? A polynomial is differentiable everywhere, in every real number, but I can keep taking derivatives forever and ever and ever. Now, eventually I'll just get 0, but that's boring. So think of e to the x, sine x, cos x. You can take derivatives forever and ever and ever, and you can evaluate every single derivative at every real number. So we say those functions are analytic everywhere. Now let's take something like the natural log. That's not even defined at 0, is it? So certainly the derivatives don't exist at 0, so we would say it's not analytic at 0, but it's analytic for every positive number. Okay, now how about something like the square root function? I can evaluate that at 0, but none of its derivatives exist at 0. So it's not analytic at 0. So analytic doesn't just mean it's differentiable. It means it's differentiable forever and ever and ever. So in other words, I can keep taking derivatives forever and ever and ever. So if f of x is analytic, meaning f of 0 exists, f prime of 0 exists, f double prime, on and on and on, forever and ever and ever, they will always exist at 0. Now, if f of x is not analytic at 0, then I need to find a number where it is analytic. And every function that I know of that I've ever worked with in my life, if it's not analytic at 0, it's going to be analytic at 1, and then that's it. You're never going to do anything else because it just gets too messy. So I want to prove this is true, and not only prove this is true, figure out, is there a formula for that an? And it turns out there isn't. It's real simple. So here's what we're going to do. Since we're using x equals 0, let's expand the first few terms just to see what it looks like. So this looks like a0 plus a1x plus a2x squared plus a3x cubed. I'll do one more, a4x to the fourth, anx to the n, and the dot, 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 because it does not stop. That's f of x. So what is f prime of x going to look like then? Well, I don't need the power series. Let's just take the derivative of this. So what would that look like if I take the derivative of this guy?
A1.
It'll look like a1, the derivative, so just a1, and then what? 2a2x, and then 3a3x squared, and then 4a4x cubed. And eventually I'll have an n x to the n minus 1, and then, okay. Now what's the second derivative look like?
2a2.
So it's 2a2, and then 6a3x, and then 12a4x squared, and then eventually n minus 1, an x to the n minus 2. We'll do one more, I think, because we want to see if we can figure out a pattern here. Then the third derivative would be 6a3, and then 24a4x, and then that goes on n minus 1, n minus 2, x to the n minus 3. Yeah, maybe we'll do one more derivative. Now, what notation do you use for anything higher than the third derivative. Do you keep putting little slashes? Because what if I want the fifth derivative? Heck, what if I want the nth derivative? I don't know how to write n slashes. If you remember, it's parentheses. That's not an exponent, that's the derivative. Okay, that's universal notation if you're doing prime. So this would be 24a4, on, and eventually n minus 1, n minus 2. Do you notice anything about that term there? What is that kind of looking like? Looks like it's starting to look like something. A factorial. Yeah, if I keep going and I take n derivatives, won't I get a factorial there? Huh. Now, let's now evaluate this at 0. By the way, what I'm showing you is true for any number we expand about. It's just we're going to use 0 most of the time. So now let's go from our original function and all of these guys. What is f of 0? What is f prime of 0? What is f double prime of 0? What is f triple prime of 0? What is the fourth derivative of it? Now, I started by saying if f is analytic. Now, don't think of f as a polynomial. No, think of f as something more complicated, like a trig function, or an inverse trig function, or a hyperbolic function, or an exponential, or a logarithmic. Think of something transcendental. And I'm saying it's equal to an infinite polynomial, and we're actually not just proving, we're coming up very, very specifically with the polynomial that it is equal to. So what would f of 0 be? Go back to there. What's f of 0? If I replace x with 0, what am I going to get? A0. Oh, okay. Yeah, that's kind of boring. What's f prime of 0? A1. A1. What's f double prime of 0?
2A2.
And the third?
6A3.
Oh, and the fourth?
24A4.
Most important thing of all. What's the nth derivative evaluated at 0? Do you see a pattern of these numbers? Is it 24, 4 times 3 times 2 times 1? Because that's just what it came up with. And isn't 6 3 times 2 times 1? Oh, whoops, sorry. 2 factorial. What would that be? 1 factorial. And what would that one be?
0 factorial.
0. Oh, because 0 factorial is equal to 1. Do you see a clear pattern here with factorials? So what is going to be the nth derivative evaluated at 0?
N factorial.
N factorial
AN.
times this. That's a 4. Sorry, it's not looking like 4. Times. Oh. Now, I just said every polynomial that's analytic at 0 has this form. Did I do something?
Can you move the computer?
Oh, let me bring it up. Oh, sorry. Yeah, I'll do this. Somebody's Hydro Flask. Okay. Can you see that?
Yes.
Now, in general, we always say x minus c to the n. That's true. And the proof I would be doing is the same proof with x minus c. It's just impractical to use a random value of c when you're pretty much 99% of the time going to be using specifically the number 0. So I'm showing you 0. So if I go back to here, do I know what an actually is? Yes, I do. What's an? It's equal to the nth derivative evaluated at 0 over n factorial. Whoa. That's what it is equal to. Now, let me step back for a moment. Let me throw a what if at you. What if we were expanding x minus c? And so instead of 0, we were using c. Then everything I did was the same, and everywhere you see an x, you'd see an x minus c instead. And when I evaluated, I wouldn't evaluate at 0, I'd evaluate at c. Which means that the general case is the nth derivative evaluated at c. That's what every textbook will have, and that is absolutely correct. It's just c is not going to be an arbitrary term. C is going to be 0 almost 100% of the time, and the rest of the time it's going to be 1. Everybody got that? So that's why I'd rather just show you what it looks like. That means going back to here, my power series is exactly the nth derivative evaluated at 0 over n factorial x to the n. Whoa, that is crazy. That's very cool though. So let's start with the most important of all the power series. Where's the zero? It's up there. No, it's actually okay. So the most important of all the power series we consider is e to the x. So let's start with f of x equals e to the x, and we're going to expand about x equals 0. Why? Because we can. If I consider derivatives of e to the x, I can evaluate them at any real number, agreed? But if I evaluate the derivatives of e to the x at any number other than 0, then I get really icky numbers involved in the problem. But if I evaluate at 0, I get 1s. So that's much nicer. So f prime of x, let's see, that would be, let's see, what's f prime of x? Oh, that'd be, okay. And the second derivative would be
E to the x.
e to the x. In fact, let's just go ahead and say in general. Can I say the nth derivative is e to the x?
Yeah.
Yeah, we really like e to the x because it's very friendly. All right, so now we consider the derivatives. So what is f of 0? What's f prime of 0? What's f double prime of 0? And if we see a pattern, so f of 0 is, I believe, 1. And the second derivative, first derivative is 1. And the second derivative is 1. In fact, in general, the nth derivative is 1. That's why we use 0, because it's friendly for the computation part. So e to the x is analytic at all real numbers. That's why we're choosing 0. E to the x and all of its derivatives, when evaluated at 0, give me back 1. So that means that the an, the nth coefficient, is exactly what? According to that formula, it's going to be this over this. That's interesting. So that means then that e to the x equals the sum from n equals 0 to infinity of 1 over n factorial x to the n. Whoa, I think we used this one last day, perhaps. Now, I want to demonstrate why this is true. Did we do the derivative of this function last day? I can't remember. Somebody look back in their notes. Did we differentiate this specific power series? Not e to the x, this power series right here. Did we take its derivative? I thought we may have, but I'm not sure. So what does this look like? Well, this looks like, if n is 0, it's 1, plus 1 times x, all right, 1 over 1 factorial x, plus 1 over 2 factorial x squared, plus 1 over 3 factorial x cubed, 1 over 4 factorial x to the 4, 1 over n factorial x to the n. All right, that's what we're saying this is equal to. Well, just to be sure, let's take the derivative of this, okay? So if I take the derivative of this, okay, I want you to differentiate the power series. But I don't want you to differentiate it here. I want you to differentiate it right here. Okay, so let's take the derivative. So it would be 0 plus what? 1. Now when I bring down the 2, it's going to cancel with the 2 factorial, leaving me 1. When I bring down the 3, it's going to cancel with the 3, leaving me just 2 factorial, right? Everybody see that? When I bring down the 4, it's going to cancel with the 4, leaving just 3 factorial. I think I see a pattern here. Do you notice anything? We're getting all the exact same terms back, aren't we? Why is that? Because the derivative of e to the x is e to the x. This is actually a really simple proof that if you didn't know that this was e to the x, and I said, write the first several terms, now take the derivative, and you see I'm getting the exact same thing back again. Why is that? Because then you'd say, clearly this must be e to the x, because it equals its own derivative. Now we derived it this way. This is what is called, by the way, a Taylor series. These are the most important kind of power series. If I just made up some formula for the nth term, and I said, let's go x minus 5 to the nth power, and I just make up something, that's a power series. It's legitimate, it's valid, but there's no function that it came from. There's only a handful of functions that we use, right? E to the x, sine, cosine, inverse tan, log. That's pretty much it. We don't really do many more than that. If I then take their derivatives, I look for a pattern, I can write the power series. Now the key here is the pattern part. Being able to see a pattern. This was rather easy. It's not a pattern of the derivatives, it's a pattern of the constants. This was actually fairly simple. We're going to do a few others today just so you can see how this works. But the key is being able to recognize a pattern. Now we talked about this when we first started with sequences. Remember I said the ability to recognize a pattern? Really it's only the obvious ones. Now in my Math 255 class they're doing the same thing. They're having to take multiple derivatives and hopefully see a pattern. So the question is always, how many derivatives do I have to take to find the Taylor series? The answer is yes. You keep going until what? You see a pattern. That's it. If you don't see a pattern, then you can't answer the question. But there will always be a pattern if you have a friendly function. Okay, you can make things complicated. We don't want to do that. Now, here's the beautiful thing about the Taylor series. I can now tweak this if I choose to. Okay, now, I don't need you to memorize this, but you're going to be very familiar with this because I said this is the most common one used. All right? Let's find the power series for how about e to the 4x? Well, I can start by taking derivatives and do the exact same thing. Everybody agree? I can do the same thing. So when I take derivatives of e to the 4x, won't I have 4's show up as coefficients, and then 4 squared, and then 4 cubed, and 4 to the 4th? Does everybody agree with that? Or I can just go directly and write it down. You see, that's the argument. That's the argument. I just changed the argument to 4x. Can I simply do this? What do you think? Well, you'd like to. If I expand these, won't I get a 4 and then a 4 squared and then a 4 cubed and then a 4 to the 4th in front of the x's? Well, if I take derivatives of this, isn't that exactly what I'm going to get? Yeah, these are exactly the same thing. And in fact, let's go a step further because this is the most important part. You're going to like this. There are an infinite number of different Taylor series out there, but there's only a handful that we need to know. Like I said, e to the x, sine x, cos x, and everything else is a tweakage, meaning I don't actually have to do derivatives. So here's the way I like to say it. E to the thing, like using formal mathematical notation here. E to the thing is equal to 1 over n factorial times thing to the n. Well, that's what we just did, isn't it? So what if I wanted the power series for something more complicated? How about the power series for e to the, I don't know, x cubed? Now, I can do the Taylor series. Taylor series means you're taking derivatives. I can do the Taylor series, right? I can take the first derivative of that. There's a little chain rule involved. And then the second derivative will be some chain rule and product rule. And then the third derivative will be more chain rules and more product rules. And pretty soon my derivatives are going to fill up the board, aren't they? They're going to be very, very long and not very fun. Or I can just write down the answer without doing anything. Why? Because e to the x is analytic everywhere. Maybe want to try this? It's going to go here. X cubed to the nth power. That's it. You like that? You should. So why would we even care about something like this? Derivatives aside, yeah, we can all take the derivatives of this. It's not a lot of fun. We can all do that though. What if I want to integrate this? Kind of stuck because I can't. I'd like to integrate it, but I can't. It doesn't have an antiderivative. But this is a polynomial. I can integrate this. Does that make sense? So now I'm going to do something here. Give me just a moment. I'm going to show you something on, this is why we do this. It's so incredibly powerful. Okay. Now, I would like to be able to do this. I'd like to be able to leave the screen down, but I don't know if I can. This thing's. Tell you what, one of you try to. You go ahead and first. Oh, never mind. You've got an aura. Clearly, you threatened it. Every time I do that, I'll ask a student to do it, and they make a mean face, and it works. I don't know how that. It's awesome. Okay, so what we're going to do. I was watching someone do a lecture the other day, and they didn't pull the screen down. And then they could write on the board where the projection was. I thought it was great, except for the fact that it was really hard to see clearly. Because when you're projecting directly onto the whiteboard, you gain the advantage of being able to write on the whiteboard, but it's not as clear of a screen. You know, kind of works both ways. All right. All right, let's start with something simple. Y equal to e to the x. Okay, I got that. That's what we were just looking at. Those are the first three terms of the Taylor series for e to the x. Obviously, these are quite different. Do you agree? Right. In fact, I'll write it like this. Now I just added a third term. Okay, well that's kind of interesting. Just for fun, let's do one more term. Okay, now I just added a fourth term. Now, that blue thing is it's called a quartic. It's a fourth degree polynomial. Okay, cool. But I want you to notice something. I'm going to zoom in a little bit. Sort of between here and here, can you clearly distinguish the red and the blue? What do you think? Or do they kind of write each other for a while? In fact, where are they closest? Well, they're going to be closest when x is 0. And the reason is because we expanded at about 0. So whenever we're doing a series, the number you're expanding about is going to be where it's closest. So here's what I like to do. Get out your calculators, please. We're going to do a simple calculation. Okay. E to the x, and this, I'm going to give it a name. It's called P4, or the fourth degree polynomial. And it's 1 plus x plus 1 over 2 factorial x squared, 1 over 3 factorial x cubed, 1 over 4 factorial x to the fourth. This is a fourth degree polynomial. Okay, there's nothing clever about it. All right? I would like you to pick a small number, not 0, because I know if I evaluate both of these at 0, we're going to get the number 1. That's not interesting. So let's take a number that's close to 0, a small number, maybe, let's start with like a half, okay, 0.5. So I'd like you to find e to the 0.5, and let's find the fourth degree polynomial evaluated at 0.5. Now, the fourth degree polynomial evaluated at 0.5, or 1/2, is actually going to give me a rational number. Okay, so I can actually give you the fraction. So let's see what we get here. All right. In this case, I think we get a terminating decimal too. Whoops, backwards, sorry. Using my cheap calculator. The polynomial is exactly that fraction. Okay, I don't really care if your calculator can give you the fraction. It's kind of nice because the answer is a fraction. Well, e to the 0.5, obviously.
Isn't it
Do I have it back? Oh,
Yeah, reciprocating.
I had it right the first time, didn't
Yeah.
I? Sorry, thank you. Is it 128, is that right?
Yeah.
Okay, so what does this give us approximately? Well, let's see. Second 0.5 is approximately 1.648721271. It's an infinite non-repeating decimal. It's an irrational number. The second one's a polynomial. It's a terminating decimal. It's exactly a fraction. Do you notice anything interesting?
It's very close for the first 4.
They agree to 3 decimals, don't they? Now, could they possibly be equal? No, that's impossible. Because one is rational, the other is irrational. An irrational number cannot equal an irrational number. Pretty darn close. Now, I don't have a calculator with an exponential key. Could I use the polynomial? Yeah, but I would be a little bit leery. You know, I only have 3 decimal place accuracy. What if I want more decimals? Anybody got an idea?
Keep expanding it.
Keep going. I only went to the 4th power. Now, I used 0.5. What if I had used, let's say, 0.1? Let's just, for fun, let's do 0.1 now. Same problem. Let's do e to the 0.1. 0.1 is small. So e to the 0.1 is approximately, and again, it's an approximation, it's not an equal. It's not possible to give an equal if it's an irrational number because you're only writing down the first several decimals. So it's approximately 1.1051709. If I want more, I need a more powerful calculator that does more digits. Now, what is the 4th degree polynomial evaluated at 0.1? Well, let's see. Plug those numbers in. I'm gonna skip the fraction part. Let's just go straight to the decimal. Okay. This decimal approximation, because this will be rounded because it goes past my screen, is what? 1.105170833. Gee, what do you notice? They now agree to the first 6 decimal places. Why do I get closer on this one? Anybody want to try? Because the number I used was closer to 0. If I used a number like 1 or 2 or 7, the further I get from 0, the less accuracy I'm going to have. But if I keep doing more terms, now, for practicality, I can't really use an infinite polynomial to do my calculations. But what we just saw was I used a 4th degree polynomial as an estimator for an exponential function, which sounds completely crazy at first, doesn't it? A 4th degree polynomial? Well, we got ridiculous accuracy. Now, if I can program a computer to do the power series, could I ask the computer to do the first 10 or 100 or 1,000 or million? I mean, we did that last week, remember? And remember how fast we were getting answers? If I want to go more places, that's actually quite easy. So what if I wanted more decimal accuracy? More terms. But if I've got a computer and I write an algorithm for a simple do loop to do this, this is actually quite trivial. So I can get accuracy. That's kind of how your calculator is doing the original calculation anyway. So we see here, the more terms we get, it's asymptotic. So here's the key here. That is the whole point. The exponential function is asymptotic to the polynomial. This, we have a really clever name for this polynomial that came from the Taylor series. It's called the Taylor polynomial. The Taylor series is the infinite sum. The Taylor polynomial is the first few terms. And the way we distinguish it, the subscript is not the number of terms, the subscript is the exponent. So if I wanted P2, P3, P10, P100, it doesn't matter what I ask for. That just simply means you're going to go to that exponent. Okay, everybody cool so far? Now, why is this so powerful? It's powerful as an estimator, sure, But when we want to do integration, and by the way, we're going to do the integration, most of that we're going to do next time. That's not part of today's lecture, that's in the applications part. But remember I just did e to the x cubed a moment ago? What if I wanted to do the integral of e to the x cubed, but I kept the numbers fairly close to 0? I could come up with the Taylor polynomial, integrate that, evaluate that, and you would find absurd accuracy. We're going to do this problem in a few days. We might get accuracy double-digit decimal places by just doing a few terms, which is kind of silly. Like, you know, I get 10, 12, 15 decimal place accuracy, but maybe only have 3 or 4 terms, because the terms are getting so small so fast, especially if I'm evaluating at small numbers. And that's actually what we do in real life. Okay? So, this is the stuff involving E. So now let me go back to the power series. This time I would like a power series not for e to the x cubed. No. E to the x cubed divided by x to the 4th. How would I do that? Oops, no, sorry. Not e to the x cubed. X cubed to the n. Can I bring this guy in? And then what would it look like? X to the 3n minus 4. I cannot evaluate that at 0 because that would be undefined, but I can evaluate it at numbers that are close to 0. And I don't have to take derivatives to get me here. So if I wanted to integrate this, let's say, that would be the scariest integration by parts I think anybody's ever seen, right? If it could even be done, I'd like to integrate that. It'd be much easier to integrate that. See, that's the whole point. I can integrate a power series because it is just a polynomial. Whoa. All right. Let's do the cosine function, because that's considered a very powerful one. By the way, I'm going to do the cosine. I'm not going to do the sine, but the derivation of the sine is almost identical because it's real similar for the derivative stuff. So we're going to do cos x, we'll say f of x equals cosine of x about, again, x equals 0 because all the derivatives exist at 0. It doesn't make sense to do it about, pi over 2 or pi or something, because now I have pi's in all my calculation. That would be kind of yucky. All right, so let's write the first few derivatives. That's probably all we need, the first 4. All right, so the first derivative is negative of the sine, then the second derivative, negative cos, and the third derivative, positive sine, and the fourth derivative, positive cos. Why do I only need to do 4? Because that pattern is going to repeat now, isn't it? Because I'm back to cosine. So that pattern is going to repeat forever and ever and ever. So, next thing we're going to do is let's evaluate at 0. And we're going to see if we can see a pattern here. All right. Cosine of 0 is?
1.
1. Sine of 0 is?
0.
0. Now negative cosine of 0, so that's negative 1. And then negative sine of 0, that's 0. And now positive cosine. Huh. What do you think? If I asked you what are the next 4 numbers? Would you say 0, negative 1, 0, and 1 again?
Yeah.
What do you notice about the odd derivatives? First of all of my odd derivatives will always be what?
0.
Well, the odd derivatives.
Sine.
They'll always involve sine. So therefore, the odd derivatives evaluated at 0 will all be 0. The even derivatives all involve cosine. So all of the even derivatives evaluated at 0 will be either 1 or negative 1. And they will alternate because of the negative sign. Well, how do I write that then? How do I come up with that, well, only the even derivative. So what if I said it this way? The 2n. So in other words, if n is 0, 1, 2, 3, 4, 5, 6, then 2n is a double. Well, let's see, when n is 0, when n is 1, when n is 2, to the n. Good. Everybody catch that? I'll do it again. This is what we call pattern recognition. We're figuring out a pattern. Clearly, only the evens are going to show up in my answer. So when n is 0, that means that there hasn't been a derivative yet. I should be at positive 1. That's negative 1 to the 0th power. But when n is 1, that means I'm on my second derivative. I have negative 1, which is negative 1 to the first power. When n is 2, I'm on my fourth derivative, and that's back to positive 1, which is negative 1 squared. And those are not the same. Having said that, can I now figure out what my coefficients are? Yes, but the coefficients are only going to be evens, aren't they? If I get that, the coefficients are only going to be evens. So I'll call it A2n. And A2n will be what? Negative 1 to the n over 2n factorial, exactly. Because that and that have to match. That means I can now say with certainty that the power series for cosine is equal to n equals 0 to infinity of this Since we're only doing evens, there are no odds, therefore there are no odd exponents, so it will still be 2n. And turns out this is considered really huge and important. But it wasn't that hard to come up with. Cosine is equal to a polynomial. I mean, does that sound completely whack to you? Cosine is equal to a polynomial? Well, let's do it. Let's show it. All right, so let's expand. What's the first term? You guys can tell me this out loud. When n is 0, it's going to be 1 over 1 x to the 0, which is what? 1. Then minus, because it's going to alternate in sign. Now when n is 1, it's going to be negative 1 over 2 factorial, x to the what power? Okay, everybody with me on that? Oh, hold on, let me bring this back up. All right, now when n is 2, positive 1 over 4 factorial x to the 4th power. Whoa. I've only written 3 terms. Now what do you notice? The red is the polynomial. What do you notice?
You're getting real close.
They're already, between here and here, they don't look much different, do they? I mean, you gotta admit, that's kind of cool. We've done very little. Now, what happens as they go further away? Oh, no. They're not even close to each other. The further I get from 0, the more they drift. What if I need them to stay together longer? More terms. All right, let's do another term here. Minus, then the next one's going to be what? X to the what power? 6th power. I think you see a clear pattern over what? 6 factorial. Oh my gosh. Let's do one more because it's so much fun. Plus
X to the 8th
x to the 8th
over 8.
over 8 factorial. All right. I think we're almost getting out of control here. Look at this. Those things write each other for such a long time now. It looks like literally from about negative 2.5 to 2.5, it's indistinguishable. And you're right. So let's use our calculators to do exactly this. Let's check And again, we'll pick a small number, a number relatively close to 0. It doesn't have to be like 0.001. No, no, no. Let's say, I don't know, let's use, how about 0.2? All right? So let's do the cosine of 0.2. Now, what should we call our polynomial? I have 5 terms. Has nothing to do with it. What's the highest exponent?
6. Oh, 8.
8. So this would be P8. And I want to do 0.2. Okay? So let's start with the cosine. Make sure you're in radian mode, by the way. That does matter. It won't work if you're not in radian mode. So cosine 0.2 is approximately, all right, my calculator says 980066577. Okay, that's as far as my calculator will go. Is that right?
Mhm.
Hopefully I did that right. All right, now let's put 0.2 into that polynomial. So 1 minus 0.2 squared divided by 2 factorial plus 0.2 raised to the 4th divided by 4 factorial minus 0.2 raised to the 6th divided by 6 factorial plus 0.2 raised to the 8th divided by 8 factorial. All right. Now, does anybody have that number on their calculator yet?
Yeah.
Now we have a problem. What is it?
1.
0.9.
What's the problem? I'm saying it jokingly. It's exactly the same number, isn't it? Which means they agree to my entire calculator screen, which means they might even agree for several places beyond. So you never have to use the cosine function again. You can just use this polynomial. Well, as long as what?
Close to 0.
As long as that number's small, yeah, close to 0. You got to admit, that's kind of insane, isn't it? We just did a polynomial and got the exact same decimal value as the cosine on our calculator screens. How far do they agree? I don't know. I don't know how far they agree, but that's kind of ridiculous, wouldn't you say? Why is that? Well, think about the last term you just put in. You just did 0.2 to the 8th power. Now, this is the part I need you to understand. Let's go back and just do the last term. On your calculator, just do the last term. 0.2 raised to the 8th power divided by 8 factorial. Oops, 8 factorial. And what does your calculator screen say, by the way? It's not going to give you a decimal, it's going to give you a scientific notation answer. What is it? What is the exponent? It's on the order of 10 to the negative 11th power, which means this digit doesn't show up until the 11th decimal place. Oh, so that means that I've already got 10 decimal place accuracy. Why? Because this isn't even going to affect it until after the 10th place. What's going to happen with my next term? It's going to be about the 12th or 13th decimal place. And the next term is going to be like the 15th decimal place. So you see what's happening? The changes are starting to happen further and further out, which is why I've guaranteed. What if you don't need this much accuracy? What if you only need like 3 or 4 decimal place accuracy? Well, look at your terms. Right? Maybe I can go just to x to the 4th and get good enough accuracy. That's actually how you make your decisions when you're using the Taylor polynomials. How many terms to use? How much accuracy do you need? It's actually that simple. Oh, okay. So the next term I put up, if I wanted to know how accurate this is, then the next term would have been 10th power, correct? So if I do 0.2 and I raise that to the 10th power and then I divide it by 10 factorial, that answer's on the order of 10 to the negative 14th power. That means the next term I put will not change it until the 14th decimal place, which means this is already guaranteed 13 places. So the number on your screen that I said it might go past that, it's actually 13 decimal places correct. Whoa. And we only went 5 terms. That's why this stuff is considered so powerful and so important, because the ability to come up with ridiculous accuracy really, really simply. I mean, I need a cheap calculator to do this. Isn't that crazy? The thing about it, it's pretty cool. This is just the first thing. This is not the only thing we do. So now I want to tweak the cosine function just for fun. See, what if I had to do a derivative or an integral of something yucky? Here's what I mean by yucky. Ew. Ew, this is yucky. Would you want to integrate this? No, heck no. You wouldn't want to integrate this. That'd be awful, right? But could you give me the power series for this? Well, let's see. The power series for cosine we just figured out was okay. That's my thing, if you will. Cosine of thing, it's going to be thing to the 2n. That means the power series for this is what? What's the square root of x when you raise it to the 2n power? Wouldn't this be n? But that's not unfriendly at all, is it? Huh. Well, that's kind of weird. Okay. Let's have some fun. What I'm doing is I'm changing the problem to our new problem. In other words, I'm changing my exponent instead of 2n, I'm changing it to n. Everybody see that? Now let me go back to here.
You forgot an exponent on the second equation.
Oh, it's not digging that. I don't want an exponent. There we go.
I think you have to put brackets for the root x.
Oh, I think I have probably too much space too. Whoops. Okay, hold on. I think you're right there. It's not digging this. There we go. Okay, now this is kind of a crazy graph, isn't it? Now, the cosine of the square root of x, that just feels evil, doesn't it? Just, ugh. That's the red graph. Okay, everybody see the red graph? That's just a creepy, crazy graph. The blue graph is the polynomial, but what do you notice? And by the way, the red graph goes into the y-axis, and then there's nothing on the left because it's square root of x. So basically, the red graph starts right here, and this is the red graph, and it doesn't start pulling away till about here. Which means this simple polynomial that I just wrote, this 4th degree polynomial I wrote, is a tremendous estimator of the cosine of the square root of x. So if I wanted to integrate the cosine of the square root of x, I could integrate this simple polynomial and say, you know what, pretty darn close together. And then if I evaluate it, I know my answer is going to be very, very accurate. Now, what if I want more accuracy? More terms. You can't really graph or integrate the infinite, so what you do is you do the finite. That's why you work with Taylor polynomials. Now, statistics is all based on what's called asymptotic convergence. That I'm dealing with infinities, but I can't calculate infinities. So we do things, for example, as the sample grows, it approaches the population. That's why we use samples to estimate, not calculate, populations. And the estimation becomes unequal if I allow the limit as the sample approaches the population, even if the population is infinite. So what happens is whatever the population is asymptotic to the sample, but it gets closer and closer and closer as the sample gets bigger. This is the same type of mathematics. And they actually use Taylor series heavily in statistics. And the fun thing is, in most situations in statistics where Taylor series come up, they only use the first maybe 2-3 terms at the most, because the degree of accuracy is so good so soon that it doesn't need to get complicated. Okay? Everybody cool so far? All right, we're going to do one more example. So let's suppose that I want to work with a Taylor polynomial and use that as an estimate. So it could be something complicated. I don't necessarily need the Taylor series. Now here's the thing. If I need the Taylor series, that means I have to keep taking derivatives until I see a clear pattern for the coefficients. That may be quite difficult. In fact, I may not even be able to see a pattern. But if I want to do a Taylor polynomial, I don't need a pattern. I just need to do that many derivatives. So here's what we're going to do. Let's consider the following graph. Let's consider, how about the cube root function? Okay? Now, I want to do a couple things. I want to find, let's say, how about P4 of x? And then let's find P4 of, let's take a small number like, I don't know, 1.2. These are the three things I want to do. And then we're eventually, or two things I should say. We're going to do some graphing a little later so we can see how accurate things are. Now, I need to do this, but the key is when I take derivatives of this, I can't evaluate them at 0, can I? Let me rewrite this as x to the 1/3. So what's f prime of x? What's f double prime, triple prime, fourth? By the way, that tells me how many derivatives I need pretty much. What's the first derivative?
1/3 x negative
X to the
2/3
negative.
Okay, and then the second derivative?
2/9 x to the
5/3. And then the third derivative?
10/27 x to the negative 7/3, 8/3.
8/3, and then the, what would that be now? Negative 80/81 x to the negative 11/3. Okay. I can't evaluate these at 0, can I? Darn, we need a new number. 1. By the way, 1 is the only other number. This is why you sometimes have to use a 1. I can't do any of the derivatives at 0, but you know what? I don't think I could have a friendlier number in this case than 1, could I? So, let's write them down. What is f of 1? That's 1. What's f prime of 1? Well, that's 1/3. What's f double prime of 1? Well, that would be, what, negative 2/9. What's f triple prime of 1? That's 10/27. And finally, what's the fourth derivative evaluated at 1? Negative 80/81. I want the fourth degree Taylor polynomial that's going to serve as my estimator, if you will, for the cube root function. Okay, so here's what I can say. The cube root of x, here's how we say it, is asymptotic to the fourth. It's not equal, can't equal. It equals the infinite sum. But it's asymptotic to this, and this will be, well, let's see, what's my first number? 1 plus 1/3 over 1 factorial x minus 1. Remember, I'm expanding about 1 this time, so it's got to be x minus 1. Then what's the next one going to be? Plus negative 2/9 over 2 factorial x minus 1 squared. Plus, then what's the next number? What's the third derivative evaluated one?
10/27.
10/27 over 3 factorial x minus 1 cubed. And then finally, I think it was 80/81. 4 factorial x minus 1 to the fourth. Now, if I can simplify these fractions, I should, because it will make it easier to do the calculation. And all you need is your fraction key on your calculator, by the way. So this is 1 plus 1/3 x minus 1. Don't distribute. You got x minus 1s to powers. Just leave them as powers. Then what's this one going to be? Minus 1/9 x minus 1 squared. And then what's the next one going to be? Plus, what, 5/81 x minus 1 cubed. And then the next one, does anything cancel? Yeah, something cancels.
10/243.
What is it?
10/243.
Minus 10/243.
243.
Okay, that's my polynomial. Now, here's what we're going to do. Before we do the calculation, this will be our last time today using Desmos. I love Desmos. It makes my life so much easier. Okay. I'm gonna write it using. Oops. Let's see what does that. Okay. And then this guy. Over 3 minus x minus 1 squared over 9. Whoops, that didn't work, did it? Hold on. Oh, there we go. Plus x minus 1 cubed over, oh, sorry, I put the 5 on top. Okay. Minus, and then the last one was 10.
No, you're still in the.
Did I screw it? Oh. Thank you, Chase. Minus. One of the things I hate about some of the calculators, I haven't used the arrow key at all times. Over 243.
You need
All
lowercase
right.
x.
Did I lose something?
The x
lowercase
used to be lowercase,
Oh, that's crazy. X.
cap
So
locks.
Cap lock. My fat thumbs. There we go. Okay. Now, by the way, they're not that close to 0, are they? Is that important? No. I'm expanding about 1. So they should be really close when I'm close to 1. What do you think? Let's really blow that up. The red and the blue, that's 1 right there, okay? That's 1. What do you notice? They're really, really close, near 1, which means that the polynomial is a pretty oh, actually, did I mess something up? Oh, okay, never mind. I can't see the whole polynomial. Yeah, that's fine. Okay, so now I said let's use the polynomial to estimate the cube root of 1.2. All right, so what does that mean? That means I'm going to replace x with 1.2. I'm not replacing x minus 1 with 1.2. I'm replacing x with 1.2. So that means I'm actually going to be calculating with 0.2s, aren't I? Make sure that you do that. So the cube root of 1.2 is estimated by the polynomial evaluated at 1.2, so I replace x with 1.2. Okay, so let's do that. 1 plus 0.2 minus 0.2 squared divided by 9 plus 5 times 0.2 cubed minus 10. Now, has anybody got a number? The cheaper the calculator, probably the faster the calculation. Here's the correct way to notate it. These cannot be equal, and this is not an approximation. You're saying the actual value, I'm going to estimate, that's because it's asymptotic, and then this value is approximately what? Anybody? Tell me what you got.
1.071539.
Somebody get a different number? What'd you get?
We got 1.062650.
Yeah, that's what I got. And then 0206, that's what my calculator produced. How good of an estimator is that? I don't know. So sort of parenthetically, what is the cube root of 1.2?
1.062658.
569.
How close are they?
Pretty close.
1, 2, 3, 4, 5. They agree to the first 5 places, don't they? you gotta notice that is ridiculous, isn't it? They agree to 5 places. Yes.
And just for clarification, we just kind of picked 1.2 arbitrarily.
Yeah, I picked
down the
something
line.
that was close to
Close to 1.
1. Yeah, that's the key. if I'm too far away from 1, if I'm too far away from 1, this is the problem we face. It's not that you're going to get that you did anything wrong, it's that it's not going to be very close. What if I have to do the cube root of 3 or the cube root of, well, then more terms. Because clearly we want to expand about 1. Now, here's a hypothetical question. I want you to estimate the cube root of 7.9. Man, that's really far from 1. But isn't the cube root of 8 2? So aren't all these derivatives evaluated at 8 going to be relatively friendly? Yeah. So if I needed an estimation of a number that was closer to 8, or maybe 27 or 64, in other words, if I needed a number that was closer to another perfect cube, could I use that to come up with my polynomial instead? Yeah. I mean, we'd rather not. We'd rather use this one, but that's exactly what you could do. It's kind of a powerful thing. Okay, so the Taylor series is the power series constructed by taking the derivatives and evaluating them at the number you're expanding by. If I just gave you a random power series, it doesn't equal any particular function. We can play with it, we can figure out where it converges and all that. That was last day. But today we want to find very specific power series. And again, the main ones are things like sines and cosines and such. So if I was doing this for the sine function, would it look similar? Would the process look similar to the cosine? Yeah, except where the cosine was all the evens that we would calculate, for the sine it would be all the odds. Okay, because the derivative of sine is cosine. So all the odd derivatives would produce cosines. And there's where my 1s and negative 1s would come from. So the sine is actually similar. In fact, I'm going to tell you what the sine is. The sine of x, it doesn't start at 0, it starts the first term afterwards. So it's going to be of the form negative 1 to the n, 2n plus 1 factorial. X to the 2n plus 1. So it's very similar looking. Now, if I took the derivative of this, technically all you really need to do is bring that exponent down and cancel with that guy. What would you get? X to the 2n factorial. Gee, wouldn't that look like the power series for cosine? And isn't that what the derivative of sine should produce? Yeah, so there's a consistency there. It's beautiful consistency. Any question? Okay. This is really, really powerful stuff. But the construction of this is not complicated. There's nothing complicated about this. Now I'm going to go ahead and turn off the screen. Okay. I love doing this because there was a time when I couldn't. I'd have to draw everything by hand, and my pictures are just, I mean, I can do circles. You guys know that. But trying to do this stuff and draw accurate graphs and say, here's what it looks like. But you can see how powerful this is. So the idea of a power series is to create a polynomial that we might use to answer questions. So next day, what we're going to do is we're actually going to go back and look at limits. And say, what if we want to take a limit of something complicated, maybe something involving sine or cosine or exponential, but let's use the power series instead and see what happens. And you find that in some cases, it's actually easier to do limits when you're using a power series. I know that sounds strange. Okay, so tweakage. So I've discussed how we can tweak things. If we know the power series, the tweakage is relatively simple. Now last day, the other thing we did was we looked at geometric series, if you remember. So I want to remind you, because I gave you a little hint. So we have things of this form. We've done this proof. You don't have to prove this again. This is an absolute. This is true always? Yeah, and that's a pretty big caveat, wouldn't you say? Now think of it logically. If R were a large number, then wouldn't this be ballooning up really, really fast? I mean, think of it this way. You know, what if R is just 2? Oh, it's an exponential function and I'm adding the y values. I mean, that's going to grow ridiculously fast. But if R was 2, 1 over 1 minus 2 is negative 1/2. That's ballooning out of control to infinity. I don't think it equals negative a half. Everybody understand that? Oh, r has to be small for that statement to be true. But lastly, what we did was we played around with this and said, if I start with something like this, in this form, I can turn around and write it as a power series. And so I want to continue with that today. What if I have something like this? I've got, let's say, x squared over, let's do something really complicated. How about 81 plus x to the 4th power. I would like to write this as a power series and then also figure out the radius and interval of convergence. Yee. Well, okay, we now know that I can take derivatives of this. Right, we could do this as a Taylor series. We could take a bunch of derivatives. Are you excited to take a bunch of derivatives of this?
No.
Well, one maybe, right? But after that, you forget it. It's too ugly.
You can rewrite the bottom as 9 squared plus x squared squared.
Okay.
And
Hold that thought for a minute. We can go actually further than that.
Because then you can pull out the x squared to sort of, or at least pull out one x.
I'm not worried about that guy at all.
No.
I'm not, yeah, can I? Let's do this.
Yeah, that's sort of what I was talking about.
Yeah, I'm not worried about that anymore. It's just going to be x squared times something in the end. It's not that guy you're concerned with. It's actually that guy. I got an 81 there. How do you deal with that?
Multiply by 81?
That's just crazy.
Factor out the 81.
Oh, how about if I,
Yeah.
Oh.
1 plus x to the 4th over 81.
yeah, I'm going to write it like that. It might be easier to interpret. See, my power series is only going to involve that part, and then I'm just going to multiply that by my answer. Everybody understand? That's the easy part. That's on the outside of the sum. What's my r? Be careful. What's my r?
Negative 1 over 81.
It's negative 1 over 81, oops, x to the 4th, isn't it?
Okay. Because it's supposed to be 1 minus r, and we have a plus here. Okay.
And by the way, how often will that happen?
About half the time.
About half, yeah, this is not the special case. This is, oh, okay, it's 1 minus r. Can I write the sum now as the very next thing? Yes. Yeah. Don't take any time to write the sum. Write the sum. The part that's going to take us a little longer maybe is figuring out like the interval of convergence. I'm going to have to do a little bit of algebra, but writing the sum. So it's going to be x squared over 81. Okay. That to the n. Now I mentioned before, generally speaking, the coefficient and the x should be separate. That's why I wrote it as 1 over 81 rather than x over 81, because I really do want them separate. The x separate from the coefficient. I can definitely make that cleaner. Don't worry about this yet. We'll deal with that in a moment. Just let's look at the coefficient. Could I write that as negative 1 to the n over 81 to the n? Would that be correct? Yeah, in fact, that would be the best way I could write it, because now it's very clear that it's an alternating series. Then what about that? That part, gee, that's actually the 4n. Whoa, cool. I'm almost done. If I walked away right now, if I said anything incorrect? No. So why aren't we done? Because that stuff there I can definitely work into there. And I should. In fact, I mean, come on, 81. So one more step.
N plus 1?
Okay, so 81 to the n plus 1. You said I could write 81 as 9 squared. That would be correct. I could also write it as 3 to the 4th, and that's also correct. I don't think there would be an advantage, though. I mean, yes, it is correct, but now my exponents are more complicated, and I have to start, well, thinking. I don't want to have to think. Let's just write it down. Okay? What about the x? 4n plus 2. This is our power series. This is exactly equal to the original as long as, oh, now I gotta go back to here. As long as what? As the absolute value of -1 over 81x to the fourth is, so that means x to the fourth has got to be less than 81. Oh, by the way, which just so happens to be 3 to the fourth power. Is that a good number to have? That's an excellent number to have. Can you tell me now any boundaries on x?
X is less than 3.
X is less than 3?
Absolute value.
Absolute value of x is less than 3. Because could x be negative?
Yes.
Could x be positive? Sure. But if I say x is less than 3, that means x could go towards negative infinity. That would be a problem. Because then when I raise it to the fourth power, it'd be astronomically large. Oh. So, what is my radius of convergence? 3. What's my interval of convergence?
-3.
-3 to 3. Do I need to check the endpoints? Because this is a geometric series. Remember, a geometric series, you never have to check the endpoints. It can't converge at the endpoints. So we've said everything we could possibly say. This quotient is identically equal to this power series as long as the absolute value of x is less than 3. That's pretty powerful, huh? It's kind of cool. Okay. So stop